Hello everybody and welcome back. This is the second in a three-part video series showing you how to make your own demo boards for the 18F4550 and how to program the 18F4550. In the first video we got a LED blinking. In this video we'll add both digital and analog input to our circuit. During this video I'm going to suppose you've already watched the previous video or you have equivalent knowledge from another source. If not, please check out my website www.18f4550.com or my YouTube channel 18F4550 videos. In the third video, we're going to add USB communication. But for now, let's get to our I/O demo board diagram and parts list. Here we have our I/O demo board diagram. And I've highlighted the changes in red here that are different from the blink demo board diagram. So on the right side of the chip here, these LEDs were here before. The only difference is they were named 0, 1, 2, and 3 going upward, whereas now they're named 0, 1, 2, and 3 going downward. But the resistors that match each LED are the same. And then we've added 4 more LEDs here on pins 27, 28, 29, and 30, named LED 4, 5, 6, and 7 with the same value resistors to match. On the left side of the chip is where we have our inputs. Off of pin 2 now we have a 10k ohm potentiometer and a resistor to match. And then on pins 3, 4, and 5 we have 3 switches. Switch 1 is a slide switch, whereas switch 2 and 3 are tack switches. And of course each switch has a resistor to match. Other than that, smoothing cap, powers, grounds, programming connector, the circuit's the same as the blink demo board. Let's take a quick look at our parts list. So of course we have a perf board and then the 18F4550 microcontroller and then an IC socket for the microcontroller and a smoothing cap for that also. And then we have our 10k ohm potentiometer, pot 0. And then we have R13 to match pot 0. And then we have SW1, that's our slide switch. And here's my recommended part number. And we'll use the same slide switch part number for both the breadboard and the perf board version. For switches 2 and 3, which are tack switches, for the breadboard version and the perf board version, we're going to use a different part number. And that's simply a matter of the fact that these very nice tack switches here, which fit into perf boards very well, really don't fit into breadboards as well. So for that physical reason, we'll have to use 2 different part numbers. And continuing on, we have 3 3k ohm resistors that match our 3 switches. And then we have our 8 LEDs and our 8 resistors and a 6-pin header so we can program the 18F4550 in circuit. Here we have the breadboard version of our I/O demo board circuit. There's really not much to see here. It's pretty much the same layout as the blink demo board, only with our additional parts added. We're going to find that the additional challenge for this I/O demo board lies mostly in the software. Specifically, with the blink demo board, we only briefly touched on special function registers, whereas for this I/O demo board, we're going to have a chance to work with special function registers quite a bit more, which will allow us to configure our inputs. So let's get to writing our software. So here we are on our desktop ready to write our software. So here we have our 18F4550 blink internal clock program used in the blink demo board. So just below that here, let's make a new folder for our current project. We'll call that 18F4550 I/O demo board. And I'll copy and paste that to make our lives a little bit easier in the next steps. So now we'll go to either start or our shortcut on the desktop, mplab IDE. And then we'll go to project, project wizard, next. Double check our devices on 18F4550 and next. And make sure we're choosing microchip C18 tool suite. And next. And now we're ready to create our project file. So if we go to browse and then to the desktop and to the location that we just created, where is it? 18F4550 I/O demo board. And we'll make the project name the same. And so that's the correct location there. And we don't need to add any existing files to our project. Our software for this project will still all be just in one single C file. and finish. So now we're going to go to New File, resize things a little bit. And I'll add a comment, copy and paste 18F4550 IO demo board. .c, and then we'll save it, making sure to add the current file to the project. And we'll double check we're on the desktop, and then in 18F4550 IO demo board looks good. And we'll change the name from untitled to 18F4550 IO demo board.c. No spelling error, so we're in the correct directory, correct file name, add file to project, and we'll choose save. Now we're ready to start entering our compiler config options. So once again, remember that was under help and then topics and PIC18 configuration settings if you'd like to refer to the list of them for the 18F4550. And let's see, where is that? PIC18F4550, and there we are. But rather than retype all these in, since they're pretty much all going to be the same as in the previous project, if we simply right click on blink internal clock.c, open it with Notepad, and Control A for highlight all, Control C for copy, and then we'll paste that into iodemoboard.c, and that'll give us a good starting point for the rest of the code as well. So of course we're going to delete the internal clock.c name, and let's close out the blink internal clock directory, and we're definitely going to need the datasheet later on, so let's open that up now. Okay, so now we have our 18F4550 datasheet up and our IO demo board diagram up, and we're ready to start writing our software. So basically all these compiler options are going to be the same. We're going to leave most of these features here off, and the first three still don't matter because we're still going to use the internal clock, and then we'll leave the internal clock setting also the same. One thing we do want to note here is in this comment, if OSCON is left as default, clock speed will be 1 megahertz. Since we're using analog to digital conversion, it would be advantageous to have the clock speed be a little bit faster. So we're actually going to change the OSCON register as one of the first things we do in main, but that doesn't affect this statement here. So let's scroll down a little bit, and we're still going to need function prototypes, but our function will be different. We're not going to need a delay function anymore, but rather we will need a show byte on LEDs function. And so what we're going to do is the potentiometer here will read a value anywhere from 0 volts to 5 volts, and we're going to read that into the microcontroller on this pin as an 8-bit value. So that'll be in the range of 0 to 255. Then what we're going to do is we're going to show that value on these 8 LEDs when switch 1 is on. When switch 1 is off, we'll use switch 2 and switch 3 to actuate our LEDs. So in other words, if switch 2 is pressed, then these LEDs will be on, and if switch 3 is pressed, these LEDs will be on. So that's if switch 1 is off. If switch 1 is on, then these 8 LEDs will show the binary equivalent of a value from 0 to 255 representing the state of the potentiometer. So we'll have both, depending on the state of switch 1, we'll have both digital and analog inputs in our same demo board. So for a function prototype, when we get the analog to digital result from pin 2 here, we're going to call a function to show that 8-bit value on these LEDs. It'll be easier to write that as a separate function, and we're going to call that void show byte on LEDs. And the parameters for that will be byte, which we'll get to that in a moment, byte to show. So in addition to function prototypes, let's add a few other things here to help us out. And I'll add a comment line to make that more readable. So unfortunately, the C18 compiler, I'm not sure the reason for this, but it doesn't define an actual byte data type. So the answer to that is to use unsigned characters as 8-bit variables, in other words, as bytes. So rather than state unsigned character a number of times throughout your program, it's much easiest to basically at the top of every C18 program you write, we're going to add this line, type def unsigned character byte. And now we can just use byte as our data type when we're looking for an 8-bit variable. Next, we're going to add some pound defines to name our switches and our potentiometer and our LEDs. In the previous project, we only had 4 LEDs, and that was it. And now we have 8 LEDs and 3 different switches and a potentiometer. So rather than refer to these pins directly, let's use some pound define statements to give them some names that makes it a little bit more clear what we're referring to. So we'll put that in our define section here. Define pot 0 to be port A bits .ra0, and then pound define switch 1 to be, let's neaten up our spacing a little bit, pound define switch 1, that'll be our slide switch that chooses between whether we're in the analog input mode or the digital input mode. Port A bits.ra1, and then pound define switch 2 will be port A bits.ra2, and pound define switch 3 will be port A bits.ra3. And these names correspond to directly what the diagram has for us here. Pot 0 is on RA0, switch 1 is on RA1, and so on. So now we're going to do essentially the same thing for the LEDs, so that we can name our outputs as LEDs rather than as port B bits.rb 0, 1, 2, 3, etc. This is especially advantageous because in the first demo board, our Blink demo board, we had RB 0, 1, 2, and 3 corresponding to LED 0, 1, 2, and 3. Now our order is reversed. Generally speaking, with significant projects, you're not going to have the number of the output part exactly corresponding to an increasing count of the port bit numbers. So to make the two match up and constantly keep them straight would be confusing. So it's much better to use a pound define statement, and then we can simply look at our diagram and see LED 0, 1, 2, 3, 4, 5, 6, 7 without having to look through the port bits. So we're going to add some pound define statements here. Pound define LED 0 is going to be port B bits .rb 3, and again that follows directly from the diagram here. RB3 is LED 0, and I'm going to fast forward through the remaining 7 since it's basically the same. So the first 4 LEDs are port B bits RB3, 2, 1, and 0, and the next 4 LEDs are port D bits RD 7, 6, 5, and 4. So now that we've entered our defines and our function prototypes, we're ready to move on to main. So main's going to be quite a bit different than it was last time, so let's just delete all of main and start over fresh, and of course there is no more delay function. But we are going to need our void show byte on LEDs function. It'd be easiest to copy and paste this. And we'll come back and write that at the end. Okay, so getting into main, the first thing that we're going to do is we're going to set the clock to 8 megahertz. Now, as we mentioned in our comments here, with this clock setting choice, if the OSCON register is left as the default, the clock speed will be 1 megahertz. So how do we change it to 8? Well, let's refer to our datasheet. If we check section 2, suppose we happen to know that the OSCON register is the register we want to change from our comments up here and what we looked up last time, but suppose we didn't know that. You could either search for oscillator here, or you could look in the table of contents and go to the oscillator section. And after reading this short description, you'd pretty quickly find that the OSCON register controls your clock. So the next thing you're going to do is in the find box, you're going to type OSCON. And that's going to take you, after pressing enter a few times, eventually to a table that looks very similar to this for the OSCON register. Now, pretty much all the special function registers in the chip have a page like this in the datasheet. The format's very similar. So the idea here is, since the 18F4550 is an 8-bit microcontroller, you're going to have bits 7, they're listed MSB first, 7, 6, 5, 4, and so on, down to bit 0. And each of these individual bits within that register can be set to control what that register does based on this information here. So for example, what we'd like to do is speed the clock up from the default, and you can tell what the default values are by this information at the top here, RW, that's read or write. Some bits will be, special function register bits will be read only, some will be write, and then some will be read and write. So for example, if we wanted to know what the default is for the clock speed, if you're using the internal clock, we would look for IRCF2 through IRCF0. And here we are, IRCF2, 1, and 0. So the default is 100. So the default is 100. Again, these are listed IRCF2, 1, and 0, starting with the MSB. So this is our default here, and sure enough, there's our 1 megahertz, and it even notes that for us here, note 3, default output frequency of oscillator on reset is 1 megahertz. So we'd like to speed that up to the 8 megahertz. So what we're going to do in code is we're going to type OSCON bits.ircf2, OSCON bits.ircf1, and OSCON bits.ircf0. So let's do that. And we'll do copy and paste to make our lives a little bit easier. IRCF1 and IRCF0 is assigned. And let's comment that. So we're going to set the internal clock to 8 megahertz. So what settings are we going to use here? Well, referring to our datasheet, IRCF 2, 1, and 0, if we want the clock to be 8 megahertz, those have to be 1, 1, 1. So we're simply going to assign those bits to 1, 1, and 1. And that will set our clock as the very first thing the program does when it starts to execute to 8 megahertz. Now the next thing for us to do is set our TRIS registers, our tri-state registers that is, to input for our input pins. So that's going to be these 4 here, RA0, 1, 2, and 3. And then to output for our 8 output pins, which is going to be RB0, 1, 2, and 3, and then RD 4, 5, 6, and 7. So you might remember from the Blink demo board, we set our TRIS B bits to be output. So now we're going to set our TRIS A bits to be input. So we're going to enter TRIS A bits. And again, if you're interested in additional information pertaining to the TRIS register, or suppose we didn't know about the TRIS register to begin with, we would look under I/O ports, and you might be wondering, how in the world do we set these to input or output? Well, in this description here, you're going to see it almost immediately mentions the TRIS register. And also, as we took a look at last time, we copied out to the desktop this P18F4550 header file. Let's go ahead and open that with Notepad. And that's another way that we can check our TRIS registers. So if we search for TRIS A, and sure enough, there we are. Here's TRIS A, the entire register, or TRIS A bits. and then tris A 0, 1, 2, 3, etc. So between this .h file and the explanation in the datasheet, we'd be able to discern that we want to type the following to make these pins here input. So we're going to type tris A bits.ra0 is assigned 1. Of course, 1 is for input, 0 is for output. And then we're going to copy and paste that to make our lives easy. So tris A bits.ra1, ra2, and ra3. So set pins for pot and switches to input. I'll add a few more spaces here. And now we're ready to set our tris bits for our output pins. So similarly, we're going to type tris B bits .rb3 is assigned 0, and again copy and paste to make our lives easier. And then we're going to have tris D bits .rd 7 is assigned 0, and again this is following directly off of our diagram here. So we're going to want to set tris B bits 0, 1, 2, and 3, and then tris D bits 4, 5, 6, and 7 to output. And we're going to do that by assigning the tris register to a 0. So again, copy and paste to make our lives easy. So that's going to be RB3, 2, 1, and 0. And then for tris D, we're going to set tris D bits.rd7, 6, 5, and 4 to 0. So let's go ahead and comment that. So we're going to set pins for LEDs 0 through 3 to input with those 4 statements. And with these 4 statements here, we're going to set pins for LEDs 4 through 7 to input. Okay, now that our tris registers are configured for our digital inputs, we're going to get to the analog to digital converter configuration, which is more substantial. It'll give us a much better chance to practice working with special function registers within the 18F4550. So suppose we hadn't done analog conversion with the 18F4550 before and we didn't even know where to start. Well, again, we would go to the datasheet and we could either search at the top here, or we could go down our table of contents, and we would find pretty quickly here section 21, 10-bit analog to digital converter module. And the first thing that the analog to digital converter section does, well, it gives you a quick verbal description, or written description rather, but it immediately almost lists the control registers. And ADCON 0, 1, and 2 are the 3 control registers that we're going to set before we perform the conversion to get the conversion to give us the results that we're trying to achieve. So similar to the ASCON register, the 3 control registers have a table where each of the bits, what they are and what they do, is described, and then you're instructed on how to set them to get the ADD converter module to perform the conversion that we need it to. So let's start with the ADCON 0 register. So as we start with the MSB and work towards the LSB, we see the first 2 bits are unimplemented, so we don't have to worry about those. Then the next bit here, so this is bit 7, 6, and 5. So bit 5 is CHS3, and then we have CHS2, CH1, CHS0. So what are those all about? Well, if we look down here, we see that those are the analog channel select bits. and you'll notice that channel 0, 1, 2, etc. Here the datasheet mentions AN0, AN1, AN2. That might look familiar to you from the circuit diagram. What those are is those match this here, AN0, AN1, AN2, AN3, AN4, etc. So in other words, we have our analog input going to pin 2, which is AN0. So we want to set CHS 3, 2, 1, and 0 so that our analog channel is 0. So we're going to set CHS 3, 2, 1, and 0 to 0, 0, 0, and 0. Now in this particular case, it just so happens that the default values of those 4 bits already is what we're going to set it to. So if we didn't set it, it wouldn't matter, but it's better not to rely on the defaults for 2 reasons. One, code is more readable if you don't leave things as the default. And secondly, you never know, in a more substantial sized program, you can set things, if you're talking about something that's thousands of lines, and then much later on you might have a different function that calls something else, and it gets confusing, and you might not remember what you set earlier. So it's definitely best to set these kinds of values explicitly. So let's go ahead and do that. So we're going to type addcon 0 bits dot CHS3, and most of the time the name in the data sheet here, addcon 0, and then simply appending lower bits in lowercase rather, and then dot, and then the name here will be what we'll use in our C syntax. If we ever were wondering about that, we could always check the .h file. So for example, if we go back to the .h file and to the top, and then we search for addcon 0, sure enough, there it is. And here we are down at the bottom, addcon 0 bits. And then so we're going to use a dot to refer to this inner part of the structures and the unions, how they have them set up. So addcon 0 bits dot, and there they are, CHS 3, 2, 1, and 0. Of course the order is reversed because in C, when you list structures, you start with the LSB effectively and you work towards the MSB, whereas the PIC datasheets traditionally do it the other way around, but you get the idea. So let's go ahead and set those first 4 bits. So that's going to be addcon 0 bits dot CHS 3 is assigned 0. And once again, we'll copy and paste to make our lives easier. So we're going to comment that as set analog channel to AN0, which, as we can see from our diagram, just happens to be also port RA0 or pin 2. And since we wanted to set all those to 0, we don't even have to change the values that we're assigning to here. We can leave those all as 0. We do have to change CHS to 3, 2, 1, and 0. So we've now set our first 4 bits. Now the next 2 bits in the addcon 0 register, go done and A to D on, we're going to come back to those later. Go done actually starts the analog to digital conversion process and checks that it's complete. And A to D on we're going to enable after we've configured the other 2 A to D control registers. We'll get to that in a moment. So now let's look at addcon 1. So we have this nice table here for addcon 0. If we continue down, it's a pretty safe bet. We're going to find a table for addcon 1, and here we are. So the first 2 bits, just like addcon 0, the first 2 bits are unimplemented. And then we have 6 more bits that we're going to set. So VCFG1 and VCFG0, and then PCFG 3, 2, 1, and 0. So what is VCFG1 and what is VCFG0? Those are voltage reference configuration bits. So what the datasheet is trying to tell us here is that if we set this, we can set these to a range other than power and ground. So for example, we have our potentiometer configured here so that the highest possible voltage it could read is 5 volts and the lowest possible voltage it could read is 0. In some cases, you might want to use a different range than that, but we don't in our case. Going from power to ground is fine. So the voltage reference configuration bit for the negative source will set this bit to a 0, and that will use ground as our low-end reference. And then for our high-end reference, we'll set this bit to 0, and that will use power as our high-end reference. So we're going to type addcon 1 bits dot VCFG1 is assigned 0. And then we're going to type addcon 1 bits dot VCFG0 is also going to be assigned 0. So that's going to use power and ground as our limits for our high and low end voltage for analog input. And again, just through luck in this particular case, the default of those two values is 0, or perhaps not through luck, perhaps by a good choice on the part of Microchip when they designed this chip, but it won't always work out that way. So as a habit, we probably want to set these bits. So let's go ahead and do that. So addcon 1 bits dot VCFG1 is assigned 0. So that's going to be set A to D converter negative reference to ground. And then we're going to type addcon 1 bits dot VCFG0 is assigned 0. And that's going to be set A to D converter positive reference to power. Okay, so continuing on in our data sheet. Next thing, we get to this nice table here that explains how to set bits PCFG3, 2, 1, and 0. So what's this table all about? Well, we can see the AN 0, 1, 2, and 3 that was familiar to us earlier, and then here's the settings for PCFG 3, 2, 1, and 0. So what this table is all about is that you're choosing which pins are digital and which are analog. So let's go back to our circuit diagram here. So we'd like AN0 to be an analog input because it's coming from our potentiometer, whereas switch 1, 2, and 3 we'd like to be digital inputs. So if we look at the table here, this line matches that. AN0 is analog, and then AN1, 2, and 3, and in fact everything else all the way across are digital. So what we're going to want to do is we're going to want to set PCFG 3, 2, 1, and 0 to 1, 1, 1, and 0 respectively. And that will leave only AN0 as an analog input. So let's go ahead and do that. And once again, we'll copy and paste to make our lives easier. So addcon 1 bits dot PCFG 3, 2, 1, and 0. So that's going to be set RA0, which is also pin AN0, to analog input. All other pins digital input. That last one should be a 0. So the value that we were trying to set is 1110, going from PCFG3 down to 0. So PCFG3 down to 0, 1110. Yep, that's correct. So now that we're done configuring our pins for either input or output in either analog or digital, let's take a quick overview of the configuration that we've selected. So on the, first off, I apologize for my typo. The section in the center there in red, of course pins for LEDs 0 through 3 and LEDs 4 through 7, that should say output, not input. Sorry about that. But in any case, referring to the 16 blue arrows on the left side, those are the 16 statements that are going to determine if our pins are input or output and analog or digital. So one thing we want to bear in mind here is that the tri-state registers, in our cases we're using tris A, B, and D. Those take priority over pretty much every other register in the microcontroller as far as if a pin is input or output. So in other words, with the ADCON 1 statements, the bottom 4 blue arrows, we've set some pins, you could think of it as potentially to analog input and potentially to digital input based on what the tri-state registers are set to. But since we've set RB321 and 0 and RD765 and 4 to output, the statements at the bottom for the ADCON registers won't affect those because the tris bits registers setting those to output takes priority over the ADCON bits choosing what kind of input they would be. So in other words, on the right side of the diagram here, we've summarized our I/O pin configurations. So for RA0, starting with the left side of the chip at the top and working our way down, referring to the circuit diagram, we've set RA0, and which is a shared pin with AN0 to analog input, and we've set RA1, 2, and 3, which happen to be shared with AN1, 2, and 3 to digital input. And then on the right side of the chip, because of how we've set our tris registers, regardless of what the ADCON register is set to, starting on the right side of the chip and working our way down, we've set RB3, 2, 1, and 0, which just happen to be shared pins with AN 9, 8, 10, and 12, but that doesn't matter because of the tris register state. We've set those to digital output, and then we've also set RD765 and 4 to digital output. Okay, so continuing on with our datasheet now, we've finished with register ADCON 1, so now we're going to configure register ADCON 2, and then we'll be ready to get into actually doing the analog to digital conversion. So bit 6 here is unimplemented. Bit 7 here requires a little bit of explanation. This is ADFM A to D result format select bit. So I made this separate picture to try to explain it. And there we are. So this register here, ADCON2 bits.ADFM, this setting will allow us to choose where our analog to digital result will end up. And where the microcontroller circuitry is going to put that result is going to be in one of 2 registers. Now the issue we have here is referring to the datasheet. The PIC18F4550 is, as we see here, a 10-bit resolution analog to digital converter module, but the PIC18F4550 is an 8-bit microcontroller. So in other words, we have 10 bits, but only 8-bit registers to put those results in. So in other words, we're going to have to put that 10-bit A to D result in 2 different registers. So what we're going to do here, what the microcontroller does for us actually, is we have these 2 registers, ADR ESH, that's analog to digital result high, and then we have ADR ESL, that's analog to digital result low. So we can left justify our result, in which case the 10-bit result will appear here and then in the upper 2 bits of ADR ESL, or we can right justify the result, in which case ADR ESL will be full, and then in the lower 2 bits of ADR ESH will be the most significant of the 10 bits of result. So essentially, we have a choice. We can choose between an easy way to do it, which will give us 8-bit accuracy, or a hard way to do it, which will give us 10-bit A to D conversion accuracy. So let's consider the hard way first. So if we choose to right justify, and then we take the value in these 2 bits of ADR ESH and we multiply them by 256, and then we add that result to ADR ESL and store the whole thing in a 16-bit integer variable, then we'll essentially have an analog to digital result that could go 10 bits, anywhere from 0 to 1023. But that involves a little bit more computation, and we don't really need that much accuracy since we have 8 LEDs, and we would like those 8 LEDs to show the binary values of 0 through 255 anyway. The 2 additional bits isn't necessary. So what we're going to do is we're going to do it the easy way. We're going to left justify it. And then when we have this situation, what we can do is we can simply disregard the 2 least significant bits of the result that'll be in ADR ESL and only use the 8 that are in ADR ESH, thus essentially giving us effectively an 8-bit conversion result even though the microcontroller circuitry is really working with 10 bits. Back to our datasheet here. For this ADFM bit, we're going to want to left justify, so we're going to type addcon 2 bits dot ADFM is assigned 0. So that's going to left justify our A to D result, which effectively gives us an 8-bit A to D result in register ADRESH. That's A to D result high. Now the last two sections we have to set here are these bits TACQT, A to D acquisition time, 2, 0, 2, 1, and 0, and then ADCS 2, 1, and 0, A to D conversion clock selection bits. The settings for these bits are a little bit on the complicated side. The ensuing pages of the document here gets into them in a lot of detail. A to D acquisition time requirements. It has this graph here. Then it gets into this analog input model where it justifies some calculations. Then they discuss temperature effects, and they introduce these formulas here to calculate all that. And then they have more verbiage here on selecting and configuring acquisition time and some recommendations and so on. And then a table on it, and it goes on and on. But to make a long story short, without getting into too much detail, basically these pertain to the timing of the analog to digital converter. So you can make the timing more aggressive to try and get a faster result, or you can make the timing more conservative, which will give you a slower result but a more stable result. Now, since we're using a clock setting of 8 megahertz, which is more or less in the middle of the range of what the 18F4550 is capable of, and let's take a quick look at the oscillator configurations. So we can kind of justify that. So here's our table that explains the oscillator, or a figure rather. So if you're using the internal oscillator, you can go down to speeds in the low kilohertz range, 125 kilohertz, 31 kilohertz, etc. Whereas if you're using an external oscillator, you can end up with a clock that's as fast as 48 megahertz. We're using an 8 megahertz oscillator. We're using the fastest possible internal clock setting, which is roughly in the middle of the range of what the microcontroller is capable of, going from the fastest possible external clock to the slowest possible internal clock. So when we're looking at our A to D conversion, just as kind of a rule of thumb, for our A to D timing requirements here, if we pick values more or less in the middle, which matches our clock being in the middle, that'll give us a reasonably fast A to D conversion, but it'll still be stable at the same time. So we see the values here range from 20 down to 0. So let's choose the value 101, corresponding to 12. That'll be nice and in the middle of the range of the A to D acquisition time selection bits. And then we'll do the same thing for the A to D conversion clock selection bits. We'll choose 101, which will be FOSC divided by 16, which is roughly in the middle of the range from FOSC divided by 2 to FOSC divided by 64. So you can read these following pages of the data sheet if you'd like to get into that in more detail, if you ever have really demanding A to D time requirements. But for us for now, it's really not much of an issue. Just kind of picking nice mid-range values will work well for us. So let's enter that. Addcon 2 bits dot ACQT. 2 is assigned 1, and then addcon 2 bits dot ACQT. 1 is going to be assigned 0. And addcon 2 bits dot ACQT. 0 is going to be assigned 1. So that's going to set the A to D acquisition time for us. And then we're going to type addcon 2 bits adcs2 is assigned 1, and addcon 2 bits adcs1 is assigned 0, and addcon 2 bits adcs0 is assigned 1. So let's comment that, set A to D conversion clock. Okay, so now what we're going to do is we're going to go back to addcon 0. So back up here, we saw these bits earlier. We're back here at addcon 0. We saw these bits go done and A to D on. So at this point, we're ready to turn the analog to digital module on since we've completed all the other configurations. So A to D on is a typical logic high. So A to D converter module is enabled. We're going to add AD0 or ADO on rather to a 1. So let's do that. So addcon 0 bits dot AD on is assigned a 1. That's going to be turn A to D converter on. And at this point, we're done with our configuration. So we're ready to begin our infinite while loop. Before we do that, let's take a quick aside. So basically, if we had never used the analog to digital conversion features of this chip before, when we went to this section, we would have seen a little bit of verbiage on it, and then the document pretty quickly gets to mentioning the control registers. And then we have these nice tables for each register. Pretty much everything in the 18F4550 is the same idea. For example, let's say we wanted to do USB communication and we had no idea where to start. We could look in the index, find USB, and it's going to have a nice description here and some nice diagrams and stuff. And then almost immediately, it's going to get into discussing the different control registers, UCON, UCFG, USTAT, UADDR, etc. And at the end of each section in the datasheet, it's going to have a summary of all the registers that are pertaining to that functionality. So for example, the USB section is particularly long. This is kind of a preview of our third demo board here a little bit. And sure enough, here we see these other similar tables for each register. And eventually, when we get to the end of the USB section, there'll be a list of, and here we are, registers associated with USB module operations. So then at the end of that section of the document, of the datasheet, the datasheet summarizes for us all the registers that we need to be concerned with. And again, all these other functions will be pretty much along the same lines. For example, interrupts, I/O ports we've already taken a quick look at. Of course, the first thing it does is mention the tris register and the port register. Timers would be similar. For example, let's say we wanted to know how to do I2C communication. That happens to be under this section here, Master Synchronous Serial Port Module, which performs both SPI and I2C communication. But let's say it discusses SPI first and then I2C. So if we type I2C, that'll jump us down and do a few searches here. Enter a few times, that'll jump us down to I2C mode. So again, once again, it has a bit of a brief description, a nice helpful diagram here, and then it lists all the registers you need to know: SSPCon1, SSPCon2, SSPstat, SSPbuff, SSPSR, and so on. And then it describes the registers in a little bit of detail, and then we get to those same tables that tell us what each individual bit in those registers are and what we need to set them to perform I2C communication. And there's the next register and so on. And again, if we go to the end of that section, hopefully I didn't just skip by it. No, I didn't. The I2C section is also pretty long. More data on timing here. Baud rate generator, that's more I2C data. More I2C timing diagrams. But eventually we'll get to, here we are, a table registers associated with I2C operation, and then this is all the registers. These PIR, PIE are pertaining to interrupts, and then TRISC and TRISD, of course, you have to set your tri-state gates to the correct input and output, and then we have the registers that are specific to I2C communication here. SSP buff, SSP ADD, SSP-con 1, SSP-con 2, SSP stat, etc. So any of these are going to be the same idea. And in fact, if we look back to the beginning of the document and we look for special function registers, like for example the OSCON register was one of the first registers that we looked at, so let's search for that a few times, and that'll take us down to a table of all the registers if we search from the beginning of the document. And here we are. This section here, special function register map, lists all of the special function registers, and then for example in the case of the OSCON, it specifically lists these registers are implemented as static RAM in the data memory space. So it even specifically lists the location in data memory where each register is found. So this is really the magic that makes the hardware-software interface of the 18F4550 work. It's basically the same theme for any of these. You have to look up the applicable registers to what you're doing. Then you have to set the configuration bits to what you need them to be. And then you're going to manipulate certain bits within those registers as an ongoing thing when you're working with that feature. So for example, when we finish our analog to digital conversion section, which we'll get to in just a moment, we're going to need to manipulate the go done bit that we looked at earlier, and that will tell us about the timing and results and so on of our analog to digital conversion. But first let's set our digital switches. So now we're going to begin our while loop. So while 1, if switch 1 equals 1. So this is going to be if switch 1 is off. And that's logic low. I'll explain that in a moment. That means we're in digital mode. Okay, so let's take a look at our diagram. So if switch 1, if this switch is, as we just stated here, if this switch is off, we'd like to enter digital mode. And if it's on, we'd like to enter analog mode. So if we put an if statement here, if switch equals 1, if you have a software background and not a hardware background, that might seem backwards to you because we're checking if it's 1 to see if it's off. But looking at the circuit, if this switch is open, then there can't be voltage drop across R14. So pin 3 here, RA1, is going to see the full 5 volts. Whereas if this switch is closed, then there will be a voltage drop across R14, and we'll have 5 volts at the top of the resistor but 0 volts at the bottom. So therefore the 0 volts will carry over here to pin RA1, which will see 0 volts. So in other words, we have a logic low situation. If the switch is open, we're going to have 5 volts here. If the switch is closed, we're going to have 0 volts. That's unfortunately that's common in digital electronics. If you have a software background and you're not used to it, you're going to have to kind of get comfortable with that because you're going to see it often. It always helps to comment that in code so you don't get mixed up with logic low versus logic high. And you'll notice also that the other 2 switches are wired the same, so they're also going to be logic low. So now we're going to type if switch 2 is 0. So that's going to be if switch 2 is on, and again 0 is on because it's logic low. Then what we're going to want to do in that case is we're going to want to turn on LEDs 0, 1, 2, and 3. So since we had our nice pound define statements up here, we don't have to type port B bits dot RB3, port B bits dot RB2, etc. We can just type LED 0, LED 1, LED 2, LED 3. So LED 0 is going to be assigned 1. LED 1 is going to be assigned 1. LED 2 is going to be assigned 1. And LED 3 is going to be assigned 1. So let's comment that turn on LEDs 0 through 3. So now if switch 2 is off, we're going to want to leave LEDs 0, 1, 2, and 3 off. So we'll type else if switch 2 equals 1. Let's make our spacing consistent here. Else if switch 2 is off, and again that's logic low. Then we're going to want to turn LED, and I'll just copy and paste here to make this easy. Turn off LED 0 through 3. And after that else statement, now we're going to have if else statement rather, now we're going to have else. And switch 2 should either be on or off. It should never be anything else. So we should never get here. And again, if you're used to a desktop software background, this final else might seem a little odd, but I really suggest putting that in this kind of situation, because although this should never happen, if there's some kind of fault in your circuit or some timing problem happens, you'd be surprised how sometimes you can get into this situation. So for debugging, it's very helpful to leave this here. You could assign a LED to something, and then if you see that LED turn on and you know it never should when you're debugging something, then you know you got into this part of the program. So then we'll end that else. So now basically we're going to do the same thing with switch 3. If switch 3 is on, then we're going to turn on the other 4 LEDs. If it's off, then we're going to leave the other 4 LEDs off. So I'll fast forward this next part since it's essentially the same idea. Okay, so now with this closing brace, that completes the digital logic handling portion of our code. So in other words, we're now finished with the section if switch 1 equals 1, in other words, if switch 1 is off. If switch 1 is off, then we'd like to respond to switch 2 and 3 as digital inputs. If switch 1 is on, then we're going to start processing potentiometer 0's input to pin 2 as an analog input. So let's take a look at that. Okay, so else if, and again, this line here is going to match, or I should say this curly brace here matches to this one up here. So in other words, if switch 1 is off, now we're going to handle if switch 1 is on. So else if switch 1 equals 0, and again remember it's logic low, so that's going to be if switch 1 is on, then we're going to enter analog mode. So fortunately, we're actually going to have very little code necessary for our analog to digital conversion now that we've already set everything up before we entered our infinite while loop. So here's what we're going to do. we recall from earlier that when we were looking at the addcon 0 register, we had this bit go done. So first off, how are we going to refer to that bit in our C code? Because we can't have addcon 0 bits dot go slash logic low symbol done. That's not valid C syntax. So if we're ever in a situation like this, or if we wonder if the name is the same on the datasheet as how we're going to have to refer to it in code, of course we're going to go to the .h file. So if we search for addcon 0, we'll find it, and so we're going to look for something to the effect of go done, and sure enough, here it is. So that tells us that the syntax is going to be addcon 0 bits dot go underscore done to refer to that bit. So let's go ahead and enter that. Addcon 0 bits dot go underscore done is assigned. Now what are we going to assign it to? Well, if we look in the datasheet here, if we see that if we assign it to 1, conversion is in progress, and if we assign it to 0, it's idle. Now you'll notice that that bit is both read and write, and that it's set to 0, in other words idle by default. So here's what we're going to do. We're going to set addcon 0 bits dot go done to 1, and that's going to perform our A to D conversion. Then the next line that we're going to have is going to be while addcon 0 bits dot go underscore done, the same bit, while that equals 1. Now notice we have assignment here, so we're writing, and then here we have equality, so we're reading. So while addcon bits go done equals 1, so in other words while it's still what we set it to, we're going to infinitely loop. So effectively what this line is going to do is we're going to wait here until addcon bits dot go underscore done equals 0. And then at that point in the register ADRESH, that's analog to digital result high, is going to be where the result is stored. So if you're starting to pick up on microcontroller programming coming from a desktop software background, especially if you're used to a language like Java or the .NET languages, which is substantially far from compiler level, this kind of code might seem really, really weird to you. But actually, with microcontrollers, this is extremely common. What you're going to do very, very frequently for hardware-software interface stuff is you're going to set a certain bit to a certain value, and then you're going to check either that bit or another bit. And then when the bit that you're checking changes, then you know that the internal circuitry of the microcontroller has completed some process. So now that we know we have our result in address high, the last thing that we have to do is we have to show that result on the 8 LEDs that we have as an 8-bit value, and we're going to call the function that we started to write earlier to do that. So show byte on LEDs. So we could have crammed that all into function main, but it's a little bit neater, more readable to have it as a separate function. And then we're going to do the same idea as we did before. Since switch 1 is either on or off, if everything's working perfectly, we didn't need to make this an if. We could have just made this else and then eliminated this if statement. But for debugging, it could really pay some dividends for us later to make switch 1 check if it's off, then check if it's on, and then if neither of those happens, put an else clause should never get here. And we can put some debugging statements in there later to see if we are indeed getting in there, at which point we know we have some kind of problem with our switch 1 input. So then we're going to end our infinite while loop. And you'll notice MPLAB has this nice feature. If you put the cursor just next to this curly brace, it'll highlight the matching curly brace in yellow. So that tells us that we did get our spacing and everything correct, and that matches our while loop. And if we do the same thing here, now the beginning of main should be yellow, and indeed it is. So the only thing left is to write our function to show our byte on LEDs, given that we're passed in a 8-bit variable, the typedef byte variable we designed or established earlier. So that's essentially an unsigned character because of this typedef statement. Okay, so now we're going to get into another section here where if you have a desktop software background, this is going to seem a little bit weird to you. What we're going to have to do is we're going to have to do some bitwise operations on this byte variable here to see what the individual bits are. Now, those of you that have more of a digital logic background might be screaming into your monitor in another minute at me because how I'm going to do this is probably not the most efficient way to check what each individual bit is, but this will make it easy and readable. So let's go ahead and do it in favor of readability rather than in favor of efficiency. So here's what we're going to do. We're going to do if byte to show ampersand. Now notice that's a single ampersand, not a double ampersand. Of course, you're probably more used to double ampersands being comparing to conditional statements. A single ampersand is a bitwise and. So we're going to bitwise and this variable that we're passed in here, byte to show, with the mask 0B 1 and then 7 zeros. 2, 3, 4, 5, 6, 7. So what that's going to do is that's going to perform the AND operation on byte to show and this mask that we have. So since anything and 0 is always going to be cleared, because anything and 0 is 0, that's going to clear the lower 7 bits of byte to show. And anything and 1 is what the anything was to begin with. So in other words, no matter what's passed into byte to show after this bitwise operation, the result is going to be whatever the most significant bit was, the 7th bit. The bit that we're ANDing with the 1 is going to be whatever it was to begin with, and the other 7 bits are going to be clear. So we're essentially isolating the MSB. So if that equals 0B 1, 1, 2, 3, 4, 5, 6, 7 zeros. So if that equals a 1, in other words, if overall what this if statement is doing is checking if the MSB coming in is a 1, then we're going to turn on LED 7. Else the MSB must have been a 0, so we're going to turn off LED 7. Now essentially we're going to do the same thing for the other 7 bits of byte to show, those being bits 6 through 0. Okay, so now our function's complete, and what this function is going to do is it's going to show the byte that's passed in on LEDs 7 through 0 as a binary number. So at this point our entire program is complete, and we can save it and compile it and see if we made any typos, and by some unbelievable miracle I didn't make any typos the first time around. That's probably the first time that's ever happened. And there's our whole program start to finish. So if we go to the folder that we're working in on our desktop, we should see a hex file. And sure enough, there it is. And so our next step is going to be to load that hex file into our 18F4550 with either the PIC18F4550 or the PIC18F4550. Okay, so we've successfully designed our circuit and breadboarded our circuit and written our software, and now we're ready to load our hex file into the 18F4550. Please see my previous video series on the Blink demo board if you'd like more detail on how to load software with either the PIC18F4550 or the PIC18F4550 into the 18F4550. Today I'll be using the PIC18F4550. You could use the PIC18F4550 if you prefer. And we have it connected to our breadboard. So now we're going to open our PIC18F4550 programming software. And it'll take just a moment to come up. And there we are. So we see under device the PIC18F4550 auto detected, the PIC18F4550, PIC18F4550 found and connected, PIC device found. So now we're going to go to File and Import Hex, and we're going to navigate to the directory on the desktop where we got our hex file compiled to earlier, 18F4550 IO demo board. And there's our hex file. Double click on that. Hex file successfully imported, so now we're ready to write. And that'll take just a moment. Verifying device, programming successful. And so the next step here is we'll check the on power box at 5 volts and pan back down and look at our board. So with switch 1 in the off position, that's our slide switch here, we won't have any LEDs on because we're in digital mode. So if we press either switch 2 or 3, we'll see the first 4 or second 4 LEDs light up. We can even press both at the same time if we like. So that's working great. So now if we change switch 1 to on, we're now in analog mode. Now at the moment the potentiometer is turned down all the way to 0 volts. So if we slowly turn it up, we should be able to count our binary numbers on these LEDs from 0 through 255. So let's turn very slowly. I'll try and get to 1 first. There we are. 1, 2, 3, 4, 5, 6, 7, 8, and so on. So if we turn our potentiometer right about halfway up, we should see either 127 or 128 on our LEDs. Not quite there yet. And we're almost halfway, a little bit farther. And I went a little too far. And there's 127 on our LEDs. And there's 128, and as you can see, or I'm not sure how well this shows on camera, but the potentiometer is dead on halfway up now. So that's working great for us. And if we turn our potentiometer all the way up, we should get 255 on the LEDs, which of course is all of them on, and there we go. So as you can see, the response of the LEDs, if I turn the potentiometer back and forth pretty quickly, the response of the LEDs is excellent. There's really no perceptible timing delay. So those variables that we chose earlier for our analog to digital converter timing have worked out real well for us. And of course we can go back and forth to digital mode again if we like. And back to analog mode just to test the switch one more time. Still working great. So it looks like our breadboarded program and test session was very successful. Definite thumbs up on that. And now we're on to our perf board version. So now that we have successfully breadboarded and tested our circuit and software, we can move on to our perf board version. If you're relatively new to soldering and perf boarding, for example, if the Blink demo board was the first circuit you had perf boarded, this would be a great second circuit to perf board. Compared to the Blink demo board, we have some additional parts on our board and some additional traces and wires to run, but our board is still relatively uncrowded, leaving us plenty of room to work with. And so once we've successfully perf boarded our circuit, we can load our software into the 18F4550 and test. So here we have the perf boarded version of our circuit, and of course we have our trusty PIC18F4550. So we're going to plug our PIC18F4550 into the 6-pin programming header on our board. And there we go. So now we're going to go to our desktop software to load our hex file into the PIC18F4550. Final tripod adjustment there, that's good. And PIC18F4550 takes just a moment to come up. And we can see our 18F4550 has been auto-detected. PIC18F4550 found and connected. PIC device found. File import hex. Same hex file as before. It'll take just a moment to write. And programming successful. Now we'll turn the power on at 5 volts and pan back down to our circuit board. And get zoomed in on this nice. And that'll work. So with switch 1 in the off position, we're now in digital mode, so we can actuate our 8 LEDs with our 2 nice tack switches. And if we enter analog mode, we can sweep our potentiometer from 0 all the way up to 255. And there we go, and we can sweep back down to 0 if we like. And then we can go back to digital mode, and that still works great. So our perf board test is complete and a definite thumbs up. Congratulations! You now know how to make a demo board and write software for the 18F4550 with both digital and analog input. So what's next? In our third demo board video series, we'll add USB communication with a desktop or portable computer. Stay tuned.